Okay, so we can look at a general formula for half-life. And so we looked at mass over time. So m of t equals m naught times 1/2 to the exponent t over d. And again, please don't try to memorize this equation. Everything came from y equals a times b to the exponent x. And as long as you understand what each of these values here mean, it's pretty straightforward to come up with any of these formulas. Okay? So a, much like m naught, represents the initial mass. B is your growth or decay ratio. Because it's decreasing over time, we know that you have a decay ratio of 1/2. T represents your time, and D represents the half-life as opposed to your doubling time that we saw earlier. So the way this equation is written is exactly the same as the doubling time problem we looked at, except, like I said, we looked at a mass over time, and again, please don't memorize this formula. Just remember what the original formula is that we looked at, which is y equals a times b to the exponent x. Now, again, remember, the key thing I want you to remember is that t and d have to have the same units. So the time you're looking at and your half-life or your doubling time have to have the exact same units in order for you to evaluate. Okay? So that's pretty much it for the different kinds of problems that you might see that are kind of unique. Now, the next example we're going to do is a little bit different. And you're looking at a general problem, in this case, that looks at either exponential growth or decay. And so it says the population of a small town increases. So automatically, because I know it's increasing, it tells me that I'm going to have an exponential growth problem. And it's increasing at a rate of 4.3% every 6 months. Now this is a little bit weird. So it's telling me the rate at which it's increasing is 4.3%. And the frequency of how often it's happening is every 6 months. So it's not happening on an annual basis. It's happening every 6 months. And then it says if the initial population of the town is 10,543, A, determine an equation that models the growth in the population. So think about what your independent and dependent variables are. I know that my independent variable is time because the population is changing over time. And I know the dependent variable is population. So let's start with y equals a times b to the exponent x. And I know I'm looking at a population over time. And that's going to equal the initial population, which is 10,543. And now I need to figure out what my growth ratio is going to be in this case. And my growth ratio is based on my growth rate. So the ratio that I need here for the value of b is going to equal 100% of the amount that it is before plus my growth rate. And in this case, my growth rate as a decimal would be 0.043. So all I did here is I rewrote 4.3% as a decimal. And that tells me how much more I'm going to get every 6 months in terms of the population. So my growth rate is 4.3%. My growth ratio is 1.043. Okay, so there's the value that goes inside the brackets. That's 1.043. And my exponent part is going to be t, because I'm looking at time. However, what this means is every month, if I look at time in months, this means every month the population is going to increase by 4.3%. Now, is that true? No, it's not. The population is going to increase by 4.3% every 6 months. So I need to take this time value and divide it by 6. Okay? Because it doesn't specify what my time values go by, I need to indicate that. So I need to specify that t is the time in months.